June 15, 1944, 27,000 feet above Yawata, Japan. Lieutenant Saburo Sakai watched the formation materialize through broken clouds. Silver giants, bigger than anything he'd seen over China, bigger than the American bombers that hit Tokyo in '42. His Ki-44 Shoki clawed for altitude, engines screaming at maximum power, trying to reach the lead aircraft before it crossed into its bombing run. At 23,000 feet, his controls went mushy. The thin air refused to sustain aggressive maneuvering. He had another 2,000 feet of climb left. Maybe. If he was lucky. If his engine didn't quit. The Americans cruised overhead at 27,000, barely breaking a sweat, and Sakai understood with cold clarity that he was watching a new kind of war. The fighters Japan had built to dominate the Pacific, the Zeros and Hayabusas that terrorized Allied pilots in '42 and '43. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Those aircraft belonged to a different era, a time when maneuverability mattered more than altitude, when dogfighting skill could overcome numerical disadvantage. The silver bombers carving contrails across Japan's sky operated under different rules entirely. They didn't need to outfight Japanese interceptors. They flew where interceptors couldn't reach. And when Japanese fighters did claw their way up to that thin, oxygen-starved altitude, they arrived exhausted. No energy for combat, no speed for pursuit. Just enough power left to watch 12 50 caliber machine guns rotate and track them through sights that calculated lead angle faster than any human brain could process. Every nation that built heavy bombers in 1944 followed the same philosophy. More armor, bigger guns, faster engines. Defensive firepower concentrated in manned turrets, where gunners froze at 40 below zero, sucking bottled oxygen through masks that fogged and froze, fighting in positions that demanded human endurance at the edge of survival. Boeing's engineers looked at that conventional wisdom and asked a question nobody else bothered asking. What if the gunners didn't need to sit in the turrets at all? What if pressurized comfort could produce better defensive fire than frozen heroism? What if an analog computer could calculate deflection angles that no human gunner could match? The Army Air Forces called it impossible. Too complex, too fragile, too many ways for the system to fail catastrophically. Boeing built it anyway. By June 1944, when Sakai and his squadron mates climbed toward those first B-29s over Japan, they were facing something that shouldn't have existed. A bomber defended by weapons systems controlled from pressurized crew compartments, guns that fired where computers told them to fire, not where human instinct suggested. Turrets that multiple gunners could control simultaneously, concentrating fire through a system Japanese fighter pilots had no doctrine to counter. The conventional heavy bomber concept said you survived by absorbing punishment. The B-29 concept said you survived by never getting hit in the first place. Altitude kept you safe from most interceptors. Pressurization kept your crew sharp enough to use the revolutionary defensive systems that would shred any fighter that did manage to reach you. Japan's military intelligence had been tracking American bomber development since early 1944. They knew Boeing was building something big. They knew bases were going up in India and China. They understood the strategic implications of a bomber that could reach the home islands from staging areas beyond the reach of Japanese ground forces. What they didn't understand, what they couldn't have predicted, was the defensive armament philosophy. Japanese fighter pilots trained to attack from below and behind, to exploit blind spots in turret coverage, to press attacks from angles where defensive guns couldn't traverse quickly. Enough. Those tactics had worked against B-17s and B-24s over Europe. They would fail completely against the central fire control system aboard the Superfortress. January 1940, Boeing Headquarters, Seattle. The United States Army Air Corps issued specifications for a hemisphere defense weapon, a superbomber capable of 400 miles per hour, range sufficient to carry a ton of bombs 5,000 miles, maximum bomb capacity 16,000 pounds. The requirements bordered on impossible given the technology available in early 1940, consolidated Douglas, Lockheed, and Boeing submitted designs. Lockheed and Douglas dropped out quickly. The engineering challenges exceeded what their design teams could solve within the timeframe the Army demanded. Consolidated's XB-32 design offered conventional solutions. More of everything. Bigger engines, heavier guns, traditional manned turrets that followed established doctrine. Boeing's proposal, designated Model 345, incorporated pressurization technology from their 307 Stratoliner. That civilian airliner, first flown in '39, had proven that passengers could fly at 20,000 feet in shirt-sleeve comfort, while unpressurized aircraft required oxygen masks and heated suits. The technology worked. The question Boeing asked was simple and revolutionary. Could pressurization transform combat effectiveness as much as it transformed passenger comfort? The answer required rethinking everything about bomber defensive systems. Manned turrets placed gunners in freezing, unpressurized positions because that's where the guns needed to be. You couldn't pressurize a rotating turret without massive weight penalties and mechanical complications that would make the system unreliable. The solution Boeing proposed broke that connection entirely. Put the gunners in pressurized compartments. Make the turrets smaller, lighter, more aerodynamic by removing the human occupant. Control everything remotely through electrical systems and analog computers that calculated deflection angles automatically. The Army Air Forces ordered 2 prototypes in August 1940, then added a third in December. By spring 1941, Boeing's mock-up incorporated specifications that made conservative military engineers deeply uncomfortable. 5 remotely controlled turrets, 4 in the fuselage, 1 manned position in the tail, 10 50-caliber Browning machine guns, 5 sighting stations distributed throughout 3 pressurized crew compartments, an analog computer at each station, calculating ballistic corrections in real time. The concept violated conventional wisdom about defensive armament. Gunners needed to see their targets directly. They needed to feel the aircraft's motion. They needed manual control over traverse and elevation. Remote systems introduced delays, electrical failures, mechanical complexity that would break under combat, stress. At least, that's what traditional thinking suggested. Boeing had data that suggested otherwise. The 307 Stratoliner proved pressurization worked reliably at altitude. The Norden bombsight proved analog computers could calculate complex trajectories. Naval fire control systems proved remote operation could deliver accuracy beyond human capability. The pieces existed. Nobody had assembled them into a defensive system because nobody had tried. March 1943. The first production B-29 rolled out of Boeing's Wichita plant. Defense armament differed significantly from conventional heavy bombers. Instead of gunners crouched in ball turrets and waist positions, blister windows provided mounting points for sighting stations inside the pressurized fuselage. The upper forward turret, capable of mounting 4 50-caliber guns, sat atop the fuselage just aft of the cockpit. 2 lower turrets, forward and aft, nestled against the belly. The upper aft turret covered the rear hemisphere. The tail gunner occupied his own pressurized compartment, isolated from the rest of the crew by the unpressurized rear fuselage section. General Electric won the contract to develop the central fire control system after Sperry's prototype failed testing in modified B-17s. The GE system used cell-syn motors to transmit electrical signals from sighting stations to turret controls. When a gunner moved his sight to track a target, cell-syn motors in the turret received corresponding signals and moved the guns to match. But they didn't move the guns exactly where the sight pointed. The computer interposed corrections. Ballistic correction compensated for bullet drop. At 900 yards, a 50-caliber round fired at a target at the same altitude would hit several feet below aim point without correction. The computer calculated trajectory based on range, air temperature, and the bomber's altitude, then elevated the guns to compensate. Parallax. Correction addressed the fact that gunner sights and gun turrets occupied different positions in the aircraft. A target directly ahead of the sight station might be several degrees off-center from a turret mounted 20 feet away. The computer calculated the geometric offset and adjusted aim point accordingly. Lead angle correction calculated where the target would be when bullets arrived. An enemy fighter crossing the bomber's path at 300 miles per hour needed lead. The gunner kept his sight on the target. The computer measured how fast the target moved across the sight, calculated intercept point, and adjusted gun position to fire ahead of the visual aim point. The system required the gunner to properly size the target in his sight using a ranging mechanism that adjusted twin dots until they bracketed the target's wingspan. Once locked on, the computer had the data it needed: range, closure rate, deflection angle. It calculated the solution continuously, updating gun position faster than human reflexes could manage. Training at Lowry Field, Colorado, and other facilities across the United States ramped up through late 1943. Gunners learned the system using Waller trainers, spherical projection systems that simulated fighter attacks from all angles. The transition from conventional gunnery was profound. Traditional doctrine taught gunners to lead targets manually, to judge distance by eye, to compensate for their own aircraft's motion through instinct and experience. The central fire control system demanded different skills. The gunner tracked, the computer compensated. Success required keeping the sight steady on target while the computer solved the intercept geometry. It felt wrong to experienced gunners who trusted their own judgment. The system asked them to trust mathematics instead. April 1944, Chakulia, India. The 58th Bombardment Wing completed its deployment from Kansas. 130 B-29s. More than arrived safely, fewer than planned. The journey across the Atlantic, through Africa, across the Middle East to India, had claimed aircraft to mechanical failures and weather. The Wright R-3350 engines proved temperamental. Crews learned to baby them, to monitor temperatures obsessively, to shut down at the first sign of trouble. The forward staging bases around Chengdu, China, required supplies flown over the Himalayas. The hump. Every gallon of fuel, every bomb, every spare part travelled by air transport or by B-29s configured as tankers. The logistics bordered on impossible. For every combat sortie against Japan, 7 flights over the hump were required to stockpile sufficient fuel and ordnance at the Chinese bases. June 5, 1944. The first B-29 combat mission launched from India against railroad yards in Bangkok. 98 aircraft dispatched, 77 reached the target. The mission tested systems under combat conditions. Engines overheated. Navigation proved challenging. Bomb accuracy disappointed planners. But the aircraft returned. The defensive systems worked. Thai anti-aircraft fire damaged several bombers but killed none. 10 days later, 68 B-29s took off from Chengdu, heading for the Imperial Iron and Steel Works at Yawata on Japan's home island of Kyushu. The first attack on Japan since Doolittle's raid in April 1942. The formation flew at night, each aircraft bombing individually because fuel constraints prevented the formation flying that would come later with bases in the Marianas. Japanese air defenses at Yawata had been reinforced. The 19th Air Brigade controlled the 4th and 59th Air Regiments, Ki-45 Toryu night fighters, Ki-61 Hien interceptors. The 4th Regiment, stationed at Ozuki Airfield, operated the twin-engine Toryu specifically for night operations. 35 aircraft, 25, operational. Radar was primitive, warning time measured in minutes rather than hours. 47 B-29s reached the target. Anti-aircraft fire filled the sky. Searchlights swung through the darkness. Japanese fighters climbed to intercept. The defenders initially claimed 8 B-29s destroyed, 4 damaged. Actual losses were 7 aircraft to all causes, 2 confirmed shot down. Others lost to mechanical failures, navigation errors, emergency landings in China where Japanese ground forces captured the crews and destroyed the aircraft. The loss rate was acceptable by strategic bombing standards, but the mission revealed serious problems. The Toryu night fighters were too slow to catch B-29s operating at altitude. When they did position for attacks, the remote turret system proved effective. Gunners tracked fighters through their sights, pressed firing buttons, watched tracers arc out toward targets illuminated by searchlights. Computer-aimed fire reached out to 900 yards, farther than Japanese pilots expected, farther than their own weapons could effectively engage. The Japanese post-mission analysis identified the core problem immediately. The B-29 cruised at altitudes their current interceptors couldn't sustain in combat conditions. The Toryu topped out around 25,000 feet. The B-29 operated routinely at 30,000 feet and above. Even when Japanese fighters reached that altitude, they arrived with no energy reserves, no speed for pursuit, no maneuverability for combat. August 19, 1944, a daylight mission against Yawata. This time the Japanese were ready. Better weather, better radar warning. Fighters positioned at altitude before the Americans arrived. The result was the bloodiest mission the 20th Bomber Command would fly from China. 5 B-29s shot down, 30 damaged. The formation's gunners claimed 17 Japanese fighters destroyed. The actual number was probably lower. Multiple gunners often engaged the same target. Gunners claimed fighters smoking or spinning down that recovered and returned to base, but the central fire control system proved its worth. Coordinated defensive fire concentrated from multiple turrets. Gunners in the waist blisters could take control of upper and lower turrets when attacks developed from their sectors. The nose gunner controlled forward turrets. The system allowed flexible response that conventional bombers couldn't match. Japanese pilots filing combat reports described the defensive fire as unexpectedly accurate and heavy. B-29s didn't present the vulnerable blind spots that B-17s and B-24s offered. Attacks from below met fire from lower turrets that tracked smoothly, following targets through full hemispherical traverse. Attacks from above encountered upper turrets that responded before Japanese pilots expected engagement. The deterrent effect proved as valuable as actual kills. A Ki-44 pilot, lining up for an attack from below, watching the lower turret rotate and track him before he entered effective range, faced a decision. Press the attack and accept fire from guns aimed by computers, or break off and look for easier targets. The calculation changed, the psychological pressure increased. Even when turrets weren't firing, their motion signaled alert crews ready to engage. But the missions from China revealed fundamental limitations. The logistics proved unsustainable. The bases were vulnerable to Japanese ground offensives. The range to targets in Japan stretched the B-29's capabilities even from forward Chinese airfields. The 20th Air Force needed bases closer to Japan, bases that could be supplied by ship rather than air transport, bases beyond the reach of Japanese ground forces. The Marianas Islands provided the answer. Saipan, Tinian, Guam. Invaded in June 1944, secured by summer. Naval construction. Battalions began building airfields before ground combat ended. The islands offered everything China lacked: sea-level bases with runways long enough for heavy-loaded takeoffs, deep water ports for supply ships. Distance from Japan still challenging, 1,500 miles from Saipan to Tokyo, but manageable for aircraft with the B-29's range. The first B-29 touched down on Saipan, October 12, 1944. By November, the 73rd Bombardment Wing had moved its 4 groups from the United States to the Marianas. More aircraft, better logistics, missions that didn't require flying over the Himalayas to reach forward bases. The strategic bombing campaign against Japan was about to escalate beyond anything the Japanese air defense system could handle. November 24, 1944. 111 B-29s launched from Saipan targeting the Musashino aircraft plant in Tokyo. The first major raid on the Japanese capital since Doolittle. The formation flew at altitudes ranging from 27,000 to 32,000 feet. Japanese air defense scrambled everything available: Ki-84 Hayate fighters, Ki-44 Shokis. Even older Zero naval fighters pushed beyond their operational ceilings. The Japanese defenders threw 125 fighters against the formation. They made 184 attack passes. 1 B-29 went down to a ramming attack over the target. a Japanese pilot deliberately flew his damaged fighter into a bomber, destroying both aircraft. It was the only combat loss of the mission. 5 Japanese fighters fell to B-29 gunners with confirmed kills. The other 179 attacks failed to produce additional bomber losses. The defensive system worked exactly as Boeing designed it. Turrets tracked targets smoothly. Computers calculated intercept geometry continuously. Gunners pressed firing buttons and watched 50 caliber streams reach out toward targets that expected to find blind spots, and instead found coordinated fire from multiple positions. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mission also revealed the limitations of Japanese anti-aircraft artillery. Guns designed to engage bombers at 20,000 feet couldn't reach 30,000 with sufficient velocity to damage hardened targets. Shells that did reach altitude arrived with such low energy that bomber formations simply maintained course through predicted flak zones. The explosions looked dramatic. The actual damage was minimal. Japanese commanders analyzed the mission results with growing concern. The Americans had created a bomber that operated in airspace Japanese fighters couldn't contest. The defensive armament proved more effective than intelligence estimates had suggested. The formation discipline remained tight despite sustained fighter attacks. The home islands lay open to systematic destruction by an enemy that could see but barely touch. Throughout December 1944 and January 1945, the pattern repeated. Missions against aircraft factories, missions against port facilities, missions testing tactics and refining procedures. Japanese fighter units defending Tokyo, Osaka, Kobe expanded their strength. By early 1945, 375 aircraft were assigned to home defense. It wasn't enough. The mathematics were brutal. B-29s operating at design altitude cruised at 250 miles per hour, while Japanese fighters struggled to maintain that speed at 30,000 feet. A fighter needed to position ahead of the formation, climb to altitude with enough energy reserve for combat, then execute attacks against bombers, throwing up coordinated defensive fire from 12 to 14 50 caliber guns per aircraft. The Ki-84 Hayate, Japan's finest interceptor, theoretically could reach 30,000 feet. In practice, production quality varied wildly as American bombing damaged factories and forced dispersal of manufacturing. Late production Hayates suffered from poor engine reliability, inadequate fuel quality, landing gear that collapsed on touchdown. The aircraft that could theoretically match the B-29's altitude couldn't consistently reach that performance when actual examples rolled off, bombing damaged assembly lines. Even perfect Hayates, flown by experienced pilots, faced overwhelming challenges. At 30,000 feet, the air was too thin for aggressive maneuvering. One pilot described it as fighting while holding your breath. Every control input had to be gentle, too aggressive, and the fighter would stall, spin, fall through thousands of feet before the pilot recovered control. If he recovered control, many didn't. The bombers they were trying to kill cruised in formation, maintaining station, crews working in pressurized comfort. The fighters trying to reach them were operating at the edge of their performance envelope, every moment a calculation of whether pressing the attack was worth the risk of losing control. And all the while, those remote turrets were tracking, following, waiting for the fighter to commit to an attack run that would bring it into effective range of guns that fired where computers calculated hits would occur. February 1945. Major General Curtis LeMay took command of XXI Bomber Command in the Marianas. He inherited a bomber force that dominated Japanese airspace through altitude advantage and revolutionary defensive systems, but wasn't destroying targets. High-altitude precision bombing produced mediocre results. Cloud cover obscured targets. The jet stream threw bombs miles off course. Bombardiers releasing from 6 miles up were aiming at coordinates on maps, not factories they could see. LeMay's solution shocked crews who understood what the B-29 was designed to do. Strip most of the guns to save weight, load incendiary bombs instead of high explosives, fly at 5,000 to 8,000 feet at night. Attack when Japanese defenses couldn't see the formations coming until they were overhead. The irony was profound. The airplane designed to fly higher than any enemy fighter could reach would win the war by flying lower than obsolete interceptors could safely ignore. The pressurized cabin that made 30,000-foot operations possible would become unnecessary. The central fire control system, the revolutionary technology that made defensive fire devastatingly accurate, would sit mostly unused as bombers attacked in darkness from altitudes where Japanese fighters couldn't find them without radar that barely worked. But LeMay kept the tailguns, always the tailguns, because attacks still came from behind, even at night, even at low altitude, and when they came, gunners needed weapons that could engage targets the instant they appeared in the sight. The tail position, isolated in its own pressurized compartment, retained .350 caliber guns and the computing sight that made them effective beyond human capability. March 9th to 10th, 1945. Operation Meeting House. 334 B-29s hit Tokyo at low altitude, carrying incendiary clusters designed to create firestorms in Japanese cities built largely from wood and paper. The bombers flew through searchlight beams that turned night into day, through anti-aircraft fire that destroyed 16 aircraft, through ramming attacks by pilots willing to die if it meant taking one bomber with them. Approximately 100,000 people died in one night, more than either atomic bomb would kill. The firestorm consumed 16 square miles of Tokyo. Japanese defenses optimized for high-altitude intercepts couldn't handle the tactical shift. Searchlight batteries designed to illuminate bombers at 25,000 feet couldn't track aircraft weaving through the city at 5,000. Anti-aircraft guns set for high-altitude fuses fired shells that exploded thousands of feet above attacking formations. Fighters scrambled without altitude advantage found themselves in turning fights with bombers that could see them coming and maneuver aggressively at low altitude, where the B-29's performance envelope was broad and forgiving. The defensive turrets that had proven devastating at altitude worked differently down low. Fighters approached faster, engagement windows compressed, but gunners working in pressurized comfort rested, alert, using sights that calculated deflection automatically, still maintained advantages that Japanese pilots couldn't overcome. The low-altitude missions validated something unexpected. The Wright R-3350 engines, the temperamental power plants that killed crews during high-altitude operations, finally had adequate cooling. At 5,000 feet, the atmosphere was dense, airflow over cowlings was massive, the rear cylinders that overheated at altitude stayed cool. The valves that failed from heat stress survived. The magnesium components that ignited at thin air operating temperatures remained below combustion points. The engines that were villains at 30,000 feet became reliable at 5,000, but this didn't invalidate the high-altitude concept. It simply proved the B-29 could fight across its entire performance envelope. When missions required altitude, when the tactical situation demanded operating beyond enemy reach, the superfortress still owned that airspace completely. June 1945 saw the tempo of fire raids increase. The command released 20,000 tons of incendiaries in 15 missions, 3,000 sorties. Principal targets were Tokyo, Osaka, Kobe, Sasebo, Fukuoka. As destruction of these major centers became more complete, the command turned towards secondary targets. When 444 B-29s attacked Osaka on the 15th, not one Japanese fighter rose to the attack. The Japanese air defense system had collapsed. Fuel shortages prevented training. Experienced pilots were dead. Replacement pilots lacked the skill to survive combat against formations defended by central fire control systems that made every bomber a fortress. Japan never again sent up a fighter defense of any consequence. The strategic irony lived in the space between what the B-29 was designed to do and what it actually did to win the war. LeMay's low-altitude incendiary campaign destroyed Japanese cities faster and more completely than high-altitude precision bombing ever could. The pressurized cabin, the technology that drove the entire $3 billion program, sat mostly unused during missions that burned 67 Japanese cities. Yet calling the defensive system concept a failure required ignoring what happened when commanders chose to use it. The central fire control system remained in every aircraft, even when flying at altitudes where it wasn't strictly necessary. That capability flew along on every mission, unused but present, waiting for moments when altitude advantage mattered more than payload. Those moments came more often than popular narrative suggested. Mining operations in Japanese harbors required precision placement. Those missions flew at medium altitude where bombardiers could see targets clearly, but where Japanese fighters still struggled to reach combat-loaded B-29s. Daylight raids on specific industrial targets when weather permitted used altitude to reduce losses while maintaining accuracy. The aircraft operated across its entire performance envelope from 5,000 feet in firestorm raids to 32,000 when mission requirements demanded altitude advantage. August 6th and 9th, 1945. Enola Gay and Boxcar carried atomic bombs to Hiroshima and Nagasaki, flying at 30,000 feet. No Japanese fighter got close. The interceptors that scrambled couldn't reach operational altitude before the ART B-29s were already over targets. The anti-aircraft guns that fired couldn't touch aircraft at 31,000 feet. The bombers cruised to their release points at altitudes where they were visible but untouchable, dropped weapons that ended the war, and flew home without serious opposition. The mission validated everything Boeing had envisioned. The pressurized cabin kept crews sharp for missions that demanded perfect execution. The defensive systems deterred any fighter that considered interception. The altitude capability made the aircraft nearly immune to conventional defenses. The accounting revealed both triumph and terrible cost. Total B-29s built, 3,970. Total cost, $3 billion, $52 billion in 2025 currency. Combat losses in the Pacific, 414 from all causes. B-29s lost to engine fires on the ground and in the air, hundreds. B-29s shot down by Japanese fighters at operational altitude when the defensive systems were used, negligible. From November 1944 through August 1945, B-29 gunners were credited with 914 aerial victories against Japanese fighters. The defensive systems worked. The tactics worked. The operational concept Boeing proposed worked absolutely when American commanders chose to use that capability. The post-war analysis by Japanese commanders was brutally honest. They knew what they faced. American bombers flying at altitudes their fighters couldn't effectively operate in. Protected by defensive firepower they couldn't safely approach. Delivering destruction they couldn't prevent. The remote turrets meant B-29 crews stayed comfortable through 12 to 15-hour missions. No frostbite turning fingers black and useless. No oxygen deprivation causing mistakes that killed entire crews. No electrically heated suits shorting out and leaving men hypothermic. Just comfortable crews in shirt-sleeve environments, making precise decisions and executing complex procedures, while Japanese fighters struggled thousands of feet below, visible through the bombardier's clear nose, unable to climb higher. When they did reach altitude, the central fire control system was waiting. Turrets that tracked smoothly, computers that calculated deflection faster than human brains, gunners who simply kept targets centered in their sights while mathematics solved intercept geometry. The deterrent effect proved as devastating as actual kills. Japanese fighter pilots learned which B-29s were dangerous and which were vulnerable. A stationary turret signaled casualties, hydraulic failure, ammunition exhaustion. A rotating turret, scanning, tracking, following potential threats even before they entered firing range, marked that bomber as fully operational. Avoid it. Find easier targets. The formations learned to maintain the appearance of full defensive capability, even when individual positions were knocked out. German pilots over Europe had taught that lesson. A bomber broadcasting weakness drew attacks. A formation presenting unified defensive strength forced attackers to accept risks they preferred to avoid. The B-29's central fire control system created something Japanese air defenses had never encountered, a bomber where every gun could potentially track any target. where loss of a single gunner didn't mean loss of defensive coverage because other crew members could take control, where computer-aimed fire reached out to 900 yards, farther than Japanese fighters expected, farther than their own weapons could effectively engage. The effective range advantage changed everything. Japanese pilots approaching from optimal attack angles still had to survive transit through defensive fire zones that began at ranges where they couldn't shoot back. 300 yards difference in effective range meant 3 additional seconds of defensive fire before the fighter entered its own engagement envelope. 3 seconds where 50 caliber rounds walked up toward a target that couldn't respond. The human factor proved decisive. B-29 gunners worked in pressurized comfort, rested, alert, able to focus entirely on gunnery without fighting hypoxia, frostbite, or exhaustion. Japanese fighter pilots climbed to altitude already tired from the effort, arrived at intercept point with oxygen-starved reactions, made decisions with judgment degraded by physiological stress. When both sides opened fire simultaneously, the American gunner had advantages beyond just the computer sight. He was warm, well oxygenated, functioning at peak cognitive performance. The Japanese pilot was cold, hypoxic, operating at the edge of human tolerance. The quality of decision-making reflected that disparity. The final irony of the B-29 program lived in how it succeeded. The most expensive weapons program in World War II, exceeding even the Manhattan Project, succeeded spectacularly while being used in ways its designers never intended. The pressurized cabin that drove the design was both essential and irrelevant, depending on which missions you examined. The defensive system that nearly bankrupted Boeing remained in every aircraft, waiting for the moments when altitude advantage mattered. LeMay's low-altitude campaign won the war faster than high-altitude precision bombing could have. But it won using an aircraft whose revolutionary design gave commanders options Japanese defenses couldn't counter. The paradox resolved when you understood what the B-29 actually was. Not just a high-altitude bomber, not just a low-altitude incendiary platform, but a strategic weapon that could operate across its entire performance envelope, adapting to tactical requirements while maintaining capabilities that forced the enemy to defend against threats they couldn't effectively counter. Boeing had been right about everything that mattered. Build a bomber that flies where the enemy cannot follow, and you don't need to outfight them. Pressurize the crew compartment, and defensive effectiveness increases beyond what frozen hypoxic gunners can achieve. Use computers to aim guns, and accuracy improves beyond human capability. The central fire control system didn't make B-29s invulnerable. Nothing in warfare achieves invulnerability, but it made them survivable. It closed gaps that doctrine and conventional thinking had left open. It asked computers to solve geometry that human gunners couldn't calculate fast enough. And those computers, analog devices built from motors and servos and electrical circuits, performed exactly as General Electric promised they would. Japanese fighter pilots who survived the war and were interviewed by Allied intelligence officers spoke with grudging respect about the defensive systems. The turrets tracked smoothly. The fire was accurate beyond what they'd expected. The effective range surprised pilots who thought they understood bomber defensive capabilities. The B-29 forced them to recalculate every approach, to accept risk they preferred to avoid, to acknowledge that the Americans had built something genuinely new. The technical achievement was staggering. General Electric produced nearly 4,000 fire control systems during the war. Each system comprised 5 computers, one for each sighting station, servo amplifiers, motor generators, Celsin transmitters and receivers, junction boxes, cannon plugs, turret drives, ammunition feeds. The complexity was astronomical compared to conventional manually aimed guns. And it worked. In combat, under stress, in environments ranging from tropical heat to Arctic cold, at altitudes from sea level to 32,000 feet, the maintenance burden was heavy. Crews needed specialized training. Field repairs required technical expertise that conventional turrets didn't demand. But, when the systems functioned, they functioned brilliantly. The lasting impact transcended the Pacific War. Every pressure cabin bomber designed after 1945 incorporated remote fire control. The B-29 showed that human gunners didn't need to occupy turrets to fight effectively. That pressurization improved combat performance beyond the obvious comfort factors. That computers could augment human capability in ways that changed tactical calculations. The Korean War would test the system against jet fighters. MiG-15s flying at 600 miles per hour proved too fast for analog computers designed to track targets at 350. The central fire control system that dominated Japanese piston-engine fighters struggled against swept-wing jets. But that was a different war, a different technological generation. In World War II, against the enemies it was designed to fight, the system worked exactly as promised. 3,970 B-29s built. 914 aerial victories credited to defensive gunners. 72 bombers lost to Japanese fighters in over 31,000 sorties flown from August 1944 to August 1945. The loss rate to air-to-air combat was statistically negligible when the defensive systems were used at design altitude. Boeing had promised the Army Air Forces a bomber that could fly where Japanese fighters couldn't reach. When Japanese fighters did reach that altitude, they faced defensive fire aimed by computers and delivered by rested, alert gunners working in pressurized comfort. The combination proved insurmountable for an air defense system that was running out of fuel, experienced pilots, and time. The revolution wasn't just technological, it was conceptual. Previous bomber designs accepted that defensive gunners would suffer, would freeze, would fight hypoxia, would make mistakes caused by physiological stress. The B-29 design said comfort was a combat multiplier, that rested crews fought better than exhausted crews, that warm gunners aimed more accurately than frozen gunners. The numbers validated the concept. Missions lasting 15 hours. Crews arriving at target areas alert and capable rather than exhausted and hypoxic. Gunners who could focus entirely on gunnery without simultaneously fighting for survival against cold and thin air. The performance advantage compounded across mission duration until the difference between a B-29 crew and a conventional bomber crew was the difference between fresh troops and exhausted troops. Japanese commanders understood this after analyzing early combat reports. The Americans had created a bomber whose crews arrived at targets sharper than Japanese fighter pilots, who'd spent the last 30 minutes climbing to altitude while sucking bottled oxygen and fighting hypoxia. The tactical advantage wasn't just altitude. It was the combination of altitude, pressurization, and defensive systems that made the altitude meaningful. A fighter that could theoretically reach 30,000 feet but arrived exhausted wasn't useful. A fighter pilot who could theoretically intercept at altitude but made poor decisions because of hypoxia wasn't effective. The Americans had optimized the entire system for human performance under combat stress. Japan had optimized for aircraft performance and hoped pilots could endure the physiological penalties. The result was predictable. By summer 1945, Japanese air defense had collapsed not because they ran out of aircraft, but because they ran out of pilots capable of fighting effectively at the altitudes where B-29s operated. New pilots lacked training time. Fuel shortages prevented adequate preparation. Combat attrition removed experienced leaders before they could pass knowledge to replacements. And every mission, the Silver Fortresses crossed Japanese airspace with impunity. When fighters rose to meet them, those fighters faced defensive fire that seemed prescient, turrets that rotated before the attack developed, guns that tracked smoothly through approaches that should have found blind spots. Fire that reached out farther than Japanese pilots expected and hit with accuracy that conventional defensive systems couldn't match. The technological edge was real. The training advantage was decisive. The physiological superiority from pressurization was insurmountable. Together, they created a weapons system that Japanese air defense couldn't defeat, even when they understood exactly what they faced. August 14, 1945. Japan accepted terms for unconditional surrender. The war ended. The B-29's combat record was complete. The questions about whether the defensive systems justified their cost were answered. The debates about pressurization versus conventional cruise stations were settled. The doubts about computer-aimed fire were erased. Boeing's revolutionary idea, the pressurized cabin-driving defensive systems that conventional wisdom said were too complex, too fragile, too ambitious, had worked. Not perfectly, not without cost, not without painful learning curves and tragic failures. But it worked. When Japanese fighter pilots climbed as high as their engines could take them, they looked up and watched silver fortresses own the sky they couldn't reach. And when they did reach that altitude through desperate effort and took terrible risk to press attacks, they faced guns aimed by computers and fired by gunners who were warm, rested, and alert. The strategic bombing campaign against Japan demonstrated that technological superiority, when combined with operational concepts that maximized human performance, created advantages that numerical inferiority couldn't overcome. Japanese pilots flying better than they ever had, in aircraft that represented their nation's finest engineering, couldn't defeat American crews in bombers that represented a different philosophy entirely. The B-29 proved that comfort was a weapon, that pressurization was armor, that computers could aim better than humans, that revolutionary concepts, even when they seemed impossible, sometimes worked exactly as promised when engineers had the courage to build them and crews had the skill to use them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.